Have you ever really stopped to think about what's happening when you stir salt into a glass of water? I mean, it looks like it just disappears, right? But what's really going on is it's kicking off this incredible, dynamic world of charged particles. This is the secret life of solutions, or what chemists call ionic equilibrium. And honestly, it explains so much, from how a battery works to the very chemistry of our own bodies. So let's dive in.
Right, so we all know salt dissolves in water. We see it happen every time we cook. But what does that actually mean at a level we can't see? It's definitely not just vanishing. It's going through this amazing transformation. And what's happening inside that glass? Well, that's the key to our entire story today.
Okay, so when something dissolves, it basically falls into one of two camps. First, you've got your electrolytes. Think table salt. These guys break apart into charged particles, little things called ions, and that's what lets the water conduct electricity. Then you have the non-electrolytes, like sugar. Now, sugar dissolves just fine, but its molecules stay totally intact. No ions, no electricity.
Now here's where it gets really interesting. Not all electrolytes play by the same rules. There's this super important distinction we have to make between the strong players and, well, the weak ones. Think of strong electrolytes as the all-in types. When you dissolve something like table salt, pretty much every single molecule just completely breaks apart or dissociates into ions. But weak electrolytes, they're a lot more cautious. Only a tiny fraction of their molecules actually split up, creating this really cool dynamic balance, an equilibrium, between the whole molecules and the ions floating around.
So how do we measure this? Well, chemists came up with something called the degree of dissociation, and they used the Greek letter alpha to represent it. The easiest way to think about it is like a score, from 0 to 1. A strong electrolyte, it scores super close to 1, total breakup. A weak one, it scores way closer to 0. It's just a really clean way to put a number on that strength. And let's put some real names to this, just to make it stick. In the strong corner, you've got the heavyweights, things like hydrochloric acid and sulfuric acid, real powerhouses. And in the weak corner, you've got stuff like acetic acid, which, is basically just vinegar, and carbonic acid, which is the stuff that gives your soda its fizz. They're all electrolytes for sure, but they act completely differently in water.
This whole distinction between strong and weak electrolytes, it actually leads us right into one of the most famous stories in all of chemistry, how we even define acids and bases. And it wasn't some single eureka moment. It was an idea that grew and evolved as we got smarter.
So the first big theory came from a scientist named Arrhenius, and his idea was super straightforward. He said, look, if a substance has hydrogen and it releases hydrogen ions, that's H+, in water, we're calling it an acid. And if it has this hydroxyl group, the OH, and it releases hydroxide ions, OH-, it's a base. Simple, clean, a really great starting point.
But you know how science is. The Arrhenius theory had some holes. For instance, it couldn't really explain why ammonia acts like a base, because it doesn't have that OH group at all. And that pushed chemists to look for a new theory, one that wasn't about what a molecule has, but about what it does.
And that brings us to the Bronsted-Lowry theory, which was a huge shift in thinking. It says, forget about what a molecule contains, let's focus on the action of giving and taking. An acid is simply a proton donor. A base is a proton acceptor. And since a hydrogen ion, that H+, is literally just a proton, this whole theory boils down to who's passing the proton.
This reaction here is the perfect example. You've got hydrochloric acid, HCl, and it gives its proton over to ammonia, NH3. So, under the new rules, HCl is the Bronsted-Lowry acid because it donated, and ammonia is the Bronsted-Lowry base because it accepted. See? This definition just covers way more ground.
Okay, so throughout this entire story, there's been one character in the background that is just absolutely essential to everything, and that's water itself. It's not just a boring, passive stage for all this chemistry. Oh no, it's an active and really special participant.
This is honestly one of the coolest things about water. It has this special property. The technical term is amphoteric, which just means it can be an acid or a base. It can play both roles. So in a glass of pure water, water molecules are constantly reacting with each other. It's called autoionization. One water molecule donates a proton, acting like an acid, and another one accepts it, acting like a base. How cool is that?
And this little dance that water does with itself, it reaches a balance, an equilibrium, that is so predictable and so consistent that we can describe it with a constant. We call it the ionic product of water, or Kw for short. And it's simply the concentration of those hydrogen ions multiplied by the concentration of the hydroxide ions.
At room temperature, about 25 degrees Celsius, that constant has a very, very specific value, 10 to the power of -14. I know it looks like a crazy small number, but trust me, this tiny number is one of the fundamental rules of chemistry. It governs the whole relationship between acids and bases in water, and it's the key to our grand finale.
All right, here we go. Everything we've been talking about. Electrolytes, strong versus weak, protons getting passed around, even water's secret life. It all comes together in one of the most elegant and useful tools in all of science, the pH scale.
Let's be real. Working with numbers like 10 to the -14 is just clunky and annoying. So back in the early 1900s, a chemist named Sorensen came up with this brilliant solution. He created the pH scale, which uses a negative logarithm to turn those tiny, awful numbers into a simple, friendly scale, usually from 0 to 14. It's not just some random formula to memorize. It's a tool that was invented purely for convenience.
And here's how easy it is to use. In totally pure water, the H+ and OH- concentrations are perfectly balanced, which gives you a pH of exactly 7. That's neutral. Now, if you add an acid, the H+ concentration goes up and the pH number goes down. So anything below 7 is acidic. And if you add a base, the H+ goes down and the pH number goes up. Anything above 7 is basic or alkaline. That's it.
And there's one more beautiful little piece to this puzzle. Just like pH measures hydrogen ions, there's a pOH scale that measures hydroxide ions. And because of that amazing Kw constant we saw earlier, the pH and the pOH of any solution in water will always add up to 14. Every single time. It's just this perfectly simple, constant relationship.
Okay, let's bring this all the way back around to where we started. Salt. We know that when acids and bases react with each other, they make salts. But does that mean the final solution is always perfectly neutral? Not necessarily. It really all depends on the parents, so to speak. If you have a strong acid and a strong base, they're equally matched, they cancel each other out, and you get a neutral salt with a pH of 7. But if a strong acid reacts with a weak base, the acid wins that fight, and you get an acidic salt with a pH less than 7. And on the flip side, a weak acid and a strong base, the base wins, and you get a basic salt. It's basically a chemical tug-of-war, and strength is everything.
So, let's just do a super quick flyby of the main ideas. When you dissolve stuff in water, it's either an electrolyte that makes ions or a non-electrolyte that doesn't. Those electrolytes can be strong and break up completely or weak and just break up a little. This whole idea helps us to find acids and bases as proton donors and acceptors, and we can measure all of it with the pH scale, which is just a beautifully simple tool for understanding what's going on in a solution.
Which brings me to one last thing for you to think about. You see that phrase pH balanced on stuff all the time, right? On shampoo, on skin cream. So now that you actually get the chemistry behind pH, what do you think that really means, and why would it even matter? It's the perfect example of how the secret life of solutions isn't just in a lab. It's happening all around us and even on us every single day.